Every car on Earth has a reverse gear. Every truck, every motorcycle, every riding lawnmower built in the last 100 years has one. A commercial jet weighing 400 tons does not. And yet, every single day, hundreds of those jets back away from terminal gates all over the world, smoothly, precisely, and on schedule. The engines are running, the plane is moving backward, and the pilots aren't doing it. So what is? If the engines only push forward, what's pulling this thing in reverse? Could a jet engine physically run backward? And if so, why doesn't it? What happens at a major hub when the equipment that does this breaks down mid-push? And if the answer isn't the engines, why does it sound exactly like the engines when you're sitting in seat 24C watching the terminal slide away? A jet engine works like this. Air gets sucked in through the front. It gets squeezed down, mixed with fuel, and ignited. The explosion blasts exhaust out the back. That backward blast pushes the plane forward, the same basic physics as a balloon you let go of across the room. The direction of thrust is locked in by the geometry of the machine. There is no reverse setting. Reversing isn't a gear change, it's a physics problem. But here's where it gets interesting, because thrust reversers do exist. Most commercial jets have them. They're the clamshell-shaped panels or blocker doors built into the engine nacelle, and when they deploy on landing, they redirect the exhaust forward instead of backward. The engine is still blasting air in the same direction. The reversers just bend that blast around and point it the wrong way, which slows the plane down on the runway. That loud roaring surge you hear right after touchdown? That's the reversers opening. They can cut the landing roll by around 30 to 40%. So the equipment exists. The plane can, in a sense, redirect its thrust. Why not just do that at the gate? Here's the surprise. Using thrust reversers on the ground near a terminal means blasting thousands of pounds of hot, high-speed exhaust directly toward the gate, toward parked aircraft, toward the windows, and toward every ground crew member within 100 feet. The debris risk alone, loose gravel, baggage carts, forgotten tools, could be pulled straight into the engine intake and destroy it in seconds. The heat would strip paint off adjacent aircraft. The blast pressure would blow out windows. This actually happened. It wasn't a simulation. It was a lesson learned the hard way, and it came with a very long damage report. This is the part everyone misses. Most passengers sitting on a plane that's moving backward assume the pilots hit some kind of reverse button, the engine spun up, and the jet backed away under its own power. That assumption is logical. The engines are loud. The plane is moving. The connection seems obvious. But here's the thing. The engines may not even be running during pushback. Many airlines start the pushback before engines start precisely to save fuel, cut emissions at the gate, and avoid putting debris in motion near the intake. The plane you're sitting in, rolling slowly backward away from the terminal, might have completely cold engines. The proof that the engines aren't doing this is watching it happen without them. So, what's actually doing it? That squat little machine you can see from the window if you're sitting near the front. It's called a pushback tug, and it is, in almost every way, the opposite of the aircraft it's moving. It's low to the ground, it's extremely heavy, it moves at about 3 miles an hour, and it connects to the nose landing gear in the front wheel, and physically drags the entire aircraft backward, the way a tow truck drags a car. The weight isn't an accident. To move a 400-ton aircraft, the tug needs grip. Grip comes from weight pressing down on the tires. A tug that's too light would just spin its wheels against the pavement, like trying to push a boulder with rollerblades on. So pushback tugs are built dense, with ballast engineered in, until they're heavy enough to generate the friction they need. That's why they look like something between a tank and a golf cart that gave up on its dreams. There are two main types. The conventional tug uses a tow bar, a rigid metal rod that bolts to the nose gear and transmits the pull from the tug to the plane. The tow barless tug skips the bar entirely and instead cradles the nose gear in a built-in cradle, lifting it slightly off the ground before reversing. Tow barless tugs are faster to connect and more maneuverable, which is why they're becoming more common at larger airports. The end result is the same. A machine the size of a compact SUV moving an aircraft that weighs as much as a fully loaded freighter ship. The tug operator controls the entire pushback. The pilots are passengers for this phase. They can feel what's happening, and they're watching their instruments, but they aren't steering the aircraft. That control belongs entirely to the person in the tug cab. And the bridge between the cockpit and the tug is a headset cable or a radio and a ground crew member walking beside the aircraft the whole time. That person is called a wing walker, and their job is to stay at the wingtip, watch the clearances, and stop the whole operation the moment anything looks wrong. Now here's the contrast worth sitting with. The thrust reverser, that sophisticated hydraulic system built into the nacelle of a $25 million engine, reduces landing roll from 150 miles per hour at maybe 8,000 feet down to a full stop. It handles the violent, high-speed part. The pushback tug, a machine with no connection to the aircraft's systems at all, handles 200 feet at 3 miles an hour. One system lives inside the aircraft and decelerates it from the edge of liftoff. The other is a completely separate machine that crawls backward far enough to point in the right direction. Same problem, reverse movement, solved by completely different physics at completely different scales. Military aircraft handle this differently. Fighter jets operating from forward bases or carriers often can't rely on tugs at all. Some use differential thrust, throttling one engine up slightly more than the other to steer. Some are equipped with onboard systems to manage their own ramp movement. But commercial aviation looked at all of that and decided it wasn't practical at scale. The math on a hub with 400 daily departures simply doesn't work if every aircraft needs onboard systems to handle its own ground movement. A dedicated external machine, purpose-built for the job, is faster and cheaper per operation. So that's the system that won. But the system didn't spring fully formed from an engineering blueprint. It came from failure. In the early days of aviation, planes didn't need to back up at all. Airports were open grass fields. You landed, rolled to a stop, turned around under your own power, and taxied back. There was no terminal to get stuck against. There was no jet bridge boxing you in. When commercial aviation moved into enclosed terminal buildings in the 1950s, a new problem appeared that no one had thought to solve in advance. The aircraft entered the gate nose first, and now it needed to leave the same way it came in, which meant backing out. Some early operators tried the obvious solution. They used the engines. British Overseas Airways Corporation, BOAC, the predecessor to British Airways, documented cases in the 1950s of using jet thrust to push aircraft backward or reposition them near terminals. The results were not subtle. Jet blast shattered terminal windows. It stripped paint off aircraft parked nearby. It effectively sandblasted mechanics who happened to be on the ramp. In one version of events, the damage reports from these incidents were so consistent and so expensive that formalizing a tug-only protocol became the obvious fix. The rule didn't come from a safety board sitting in a conference room. It came from people filing property damage reports and wondering how to stop doing this every week. The early tugs weren't purpose-built either. One version of the history is that ground crews improvised, modifying farm tractors and industrial forklifts until someone built a machine that was actually designed for the job. The pushback tug as it exists today didn't emerge from elegant engineering. It emerged from a series of things going wrong until the right solution was obvious. And once you know it exists, you start seeing it everywhere. That wide arc the tug makes before connecting to the nose gear isn't the operator warming up. It's a precise angle calculation. The tug is positioning itself to pull the aircraft backward on the exact heading that keeps the wingtip clear of the aircraft parked 8 feet to the right. The orange-vested person standing near the wingtip during your pushback isn't a formality. They are the physical barrier between your aircraft and a $40 million airplane parked close enough to touch if the geometry is slightly wrong. When a pilot says brakes set and then releases control, they are formally handing a 400-ton machine to a person in a vehicle smaller than a sedan. The all-clear signal the ground crew gives before the tug disconnects. That moment is the handoff. Everything before it, the aircraft is being driven. Everything after, it's being flown. The aircraft hasn't left the ground yet, but the command structure has already changed. At Frankfurt Airport during peak hours, pushback operations run at intervals of about 90 seconds on a single ramp. Each one is its own negotiation. Tug operator, wing walkers, cockpit crew, air traffic control, all coordinated for a maneuver that covers less distance than a supermarket aisle. The clunk you feel under the nose at the gate isn't something loose. That's the tow bar locking to the nose gear. The moment the most powerful machine at the airport officially depends on the most unglamorous one. An Airbus A380, the double-decker, 575-ton aircraft, requires a pushback tug so heavy that the tug itself outweighs most regional jets. A machine to move a machine, and the smaller machine is itself as heavy as a whole other airplane. Night pushbacks at busy international hubs run with no lane markings, no traffic lights, and no onboard navigation assistance. The crew works entirely on radio calls, hand signals, and wands with colored lights, the same basic tools used since the 1950s. Some airports now use electric tugs. They push a wide-body aircraft backward in near silence. If you're watching from the terminal and expecting the usual mechanical noise, the absence of it is deeply wrong feeling. It looks like something's broken. Nothing is. At gates where clearances are extremely tight, the tug operator has to disconnect on a very specific heading, called a power out, so the aircraft can roll forward under its own engine power without drifting into anything. The heading has to be right. There's no correction once the tug is gone. The tow bar connecting the tug to the aircraft has a shear pin inside it, a small metal piece designed to break if the load gets too high. That's intentional. The pin snaps before the nose gear does. It's the sacrificial weak point, engineered in on purpose, because replacing a pin costs almost nothing, and replacing a nose gear costs everything. In winter, at night, you might see steam rising from the nose gear area during pushback. That's residual heat from the wheel well meeting freezing air. It looks like smoke. It looks like something is very wrong. Every experienced ramp worker has seen it. Every first-timer has stopped and stared at it for 3 full seconds before deciding it's probably fine. Here's where the system starts to crack, though. Pushback tugs need operators. Operators need training. A hub with 400 departures needs enough tugs, enough operators, and enough coordination that nothing stalls. A single broken tug can delay 6 gates in sequence. The logistics of ground movement, not flight, not air traffic control, is one of the most consistently underestimated bottlenecks in commercial aviation. And the risk is real. Ground damage incidents, planes clipping jet bridges, tugs contacting fuselages, and aircraft too close together during pushback happen far more often than mid-air incidents. If you measure by probability of contact with another object, the most dangerous part of a flight might not be takeoff. It might be the 200 feet of backward movement before the engines are even on. The industry knows this, and quietly, it's been rethinking the whole system. Companies like Safran and Honeywell have been developing what's called e-taxi, electric motors embedded directly into the main landing gear wheels. The idea is simple. Power the wheels independently and let the aircraft move forward and backward under electric power. No tug required, engines off. Some trials have happened. The technology works. The problem is weight. Adding electric motors and the systems to run them adds enough mass to cut into the fuel savings the system is supposed to generate. The math is close, but not quite there yet. It's a 2030s conversation more than a current one. Autonomous tugs are closer. Several airports are already testing GPS-guided pushback tugs with no driver in the cab. One controller manages multiple tugs from a tablet, watching multiple pushbacks in real time, intervening if anything looks wrong. The human judgment doesn't go away. It just moves off the ramp and into a control room. Single-engine taxi is already standard at many airlines. Aircraft taxi to the runway on one engine and start the second just before the takeoff roll. Per aircraft per year, the fuel savings run into the thousands of gallons. The pushback still happens with the tug, but everything after that gets more efficient. The plane was never designed to go backward. It was designed to escape gravity, and every system on it is aimed at that one direction. Reverse is a ground problem, and the aviation industry solved a ground problem with a ground machine. Heavy, slow, inelegant, and completely disconnected from the aircraft's own power. Somewhere right now, a 500-ton aircraft is being moved backward by a machine the size of a compact car. The pilots are watching. The engines are cold. And the whole thing works because someone, 70 years ago, looked at the damage reports and decided it was better to build a very heavy tractor than to let the engines burn down the terminal.